Hi everyone, Devon here. So we're going to work through some Hardy-Weinberg problems that we talked about in recitation. Just going through them again a second time so that you can have a chance to see these in case you didn't have perfect notes or you didn't quite grasp something when we presented them the first time. So the same worksheet that you have in recitation, and we're just going to go through here. So we have two equations that we're working with. You can see the first equation written out here, and we're just talking about alleles in this equation. So in this case, the p allele you can think of it as, for a given locus, this can be allele 1, and for the other allele, it's still at the same locus. This would just be the other variant. And in some respects, we're keeping this equation very simple. This would mean that in a population, 100% of all of the alleles for a given locus are either P or Q. But obviously that means that there are only two versions. It's biallelic. You could also have systems in which there are also more than two alleles at a given locus, but in this case we're just going to keep it simple and leave it at 2. The other thing you can think about is this equation is derived directly from the fact that we have just a biallelic situation. So if you want to look at how we actually come up with this equation, then you can just think of our handy Punnett square as before, in which you had a population in which you could have some frequency in which P and Q exists from your first parent, and some frequency in which the P and Q exist as they're contributed by the other parent. This could end up making a Punnett square that looks not unfamiliar. The result of this is that this group becomes our Q squared, we see here. This group becomes our P squared, so you see here. And then we have these two remaining P and Qs, and if we add those two together, we get our 2PQ. So the important thing I think to remember from this first bit is just that these two equations, the first one here, or the bottom one here, and the one on the top, this is talking about kind of simultaneously two things. This really represents genotypic frequencies. And these don't. These aren't genotypes, these are alleles. Remember, the genotype is determined by the combination of the pair of alleles you have. So there is an allelic frequency of P or Q individually, but as those combine, P's and P's and P's and Q's and Q's and Q's, they end up making a genotypic frequency. So the way I try to think of it is that this equation is here and here. This equation is everything in the middle here. It's the result of this. And you can imagine, it's just a biallelic expansion, this second equation of the first. So there you go. These are the two we're going to work with, and I'll keep those at the top for every problem going forward. So you can see the equations that we're going to use. They're at the top here. First problem is probably the most straightforward one we can imagine. You have a population in which there are two different versions of alleles, and this will happen throughout the course of your experience with population genetics. Even though we're describing things in terms of P's and Q's algebraically, we also represent these variables of different allele versions, not just with P's and Q's. So just remember that in this situation we have to define it. It actually doesn't matter whether you define the capital D as P or Q, but for the sake of this, it's the first one. I'll make that the same thing here. And this is frequency, so 40% of the time in a population we find that allele at that locus. By default, we can use this equation, and we can put in 0.4 for P. We don't know what Q is, we're going to solve for that, but they obviously have to add up to 1. So another way of thinking of this is 1 minus 0.4, or 0.6. So we don't need to bother with this equation in this initial example. All we need to know is the initial frequency of one of the two alleles, either the P or the Q. And finally, this is obviously this Q allele. We're defined as the little d, which is what we were looking for all along. Okay, pretty simple so far. Second problem, you will again use the strategy that we used earlier, in that we can use P's and Q's. We're actually given them. We don't have to find them in this case. We're told that one frequency is 0.7 and the other frequency is 0.3. I'm going to again just sort of define what these will be so that we're on the same page. But as before, these don't have to be P and Q. You could flip them. It doesn't make, there's no reason why it has to be that way. So we have initial frequencies of alleles of 0.7 and 0.3. So great. So the question is just saying, look, you've got a pool in which you know the allele frequency. What does that mean in terms of the genotypes? That is, are there homozygous? What's the frequency in which you have a homozygous recessive, homozygous dominant, or heterozygous? And that's what we're seeing in this problem between A, B, and C. So if you want to calculate what this is going to be, you can imagine the predicted or expected outcome of that is really just a product of their individual allelic contributions. So what do we see? If you want to know the frequency with which a genotype that is big A occurs, you just need to know that big A is represented by this term in our second equation in Hardy-Weinberg equilibrium. So that's just going to be the frequency of the P allele times the frequency of the P allele. And since we've defined that already to be 0.7, it's just 0.7 times 0.7, or 0.7 squared, and that turns out to be 0.49. So a direct application of the initial equation. The second problem, very similar. Lowercase a is the same as q squared, in terms of that's the genotype as we represent it. This will equal q times q, and that's going to be defined as 0.3 squared, or 0.09. Now, the last question here, the heterozygous frequency, you can do one of two things. But the one thing you can't do is say it's not equal to 0.7 times 0.3. That is, what you can't do, don't do this, don't do this, don't do this. You can't just take A, big A, and make it representing P, and little a is representing Q. This genotype, big A, little a, does not represent just the combination of initial allele frequencies. What it represents is the Hardy-Weinberg expanded proportion, which is 2pq. Another way of saying is this would be P times Q, and you can't do that because the genotype itself includes PQ plus PQ, if you remember back to the initial Punnett squared that we just showed earlier. So make sure that you do 2PQ, and that would end up giving you the right answer, or 0.7 times 0.3 times 2. That'll turn out to be 0.42, and if you look at that, you add up 0.42, 0.09, and 0.49, and that should equal 1, and that's what we expect given this equation. Okay, so the third problem, set up similar to the previous problem. You're given 100 people, and you're given a set of numbers in which those numbers have already been calculated for the genotype. And this is just asking you if these are in Hardy-Weinberg equilibrium at all. If something is in Hardy-Weinberg equilibrium, then we should be able to do a couple of things. First of all, again, define what your terms will be. And we'll say that the big B allele is going to represent, or can be represented by its frequency by P, and that the lowercase b can be represented in terms of its frequency by Q. So we can look back to this equation and find out where this will obviously be represented as BB, like we just did in the last problem. This will be represented as lowercase b, and our heterozygous represented as 2PQ in the original Hardy-Weinberg equation. So the thing is what you're going to try to do first is just count the number of alleles that are present in terms of big B and in terms of little b, so that you can actually calculate P and Q. How do you do this? Well, you have 79 individuals that have a certain genotype, and that genotype has 2 big B's each. So if I want to know the frequency or the proportion of this allele, big B, then I need to just count all of the big B's. And where can they come from? Well, I have 79 individuals that have 2 big B's, so 79 times 2 would represent all of those uppercase B's. But then, of course, there are other places where the big B can exist. That's in our heterozygous. So we're going to add 20 of those, and that 20 is derived from the fact that there are 20 heterozygotes, but they can only contribute a single big B, so we only just leave that as 20. We're going to have to divide that by the total number of individuals in the population, except we're not going to divide this by 100 because what we have are 100 people, but what we also have, if we multiply it by 2, is 200 alleles. That is, there are 200 individual bees because everybody's a diploid. So we divide this whole quantity by 200, and that can give us the frequency of P, and it turns out to be 0.89. So likewise, you can do the same thing with Q. Q, you're just going to find who has 2 each. It's the genotype that's lowercase b are homozygous recessive. And there's just one of those, so it starts out as 1 times 2. But again, there is another way that you can get a little b, and that's from our heterozygotes, and we have 20 of those. So we can add those up, and again, we can divide that by 200, and that'll give us a frequency that you would expect. It's going to be 0.11. So these work out as nice, neat calculations. Sometimes these numbers aren't perfect and you get longer decimals. Don't worry too much about that. You can certainly round to, say, the 2nd or 3rd decimal, but in this case, it works out nice and easy. Okay, so I need to erase something here for a second. So how do we test if these are actually in Hardy-Weinberg equilibrium? Well, we've calculated what we know are sort of the observed frequencies of alleles, and if those allele frequencies are in Hardy-Weinberg equilibrium, then we can plug them back into this original equation, and it should come out to equal to 1. If they don't equal 1, then we would say that it's not in Hardy-Weinberg equilibrium. So you can just take 0.89 as your value for P and square it, and then you can add 2 times 0.89 times 0.11, that gives you your representative heterozygous expected genotypic frequency, and 0.11, and square that, and figure out what that equals. It turns out that should sum up to 1, and because it adds up to 1, we would say that this population is in Hardy-Weinberg equilibrium. Again, the sort of central premise here in the Hardy-Weinberg equilibrium is that across generations, the frequency of P and the frequency of Q do not change. And if they don't change, then we can circle back and apply that to our second equation, and we would expect that if P and Q isn't changing, then our frequencies of our homozygous dominant, homozygous recessive, and heterozygous individual genotypes are also not changing. And that's what we see here. So we find that P and Q are what they are. We find that the equation did sum up to 1. That is, when we added up P squared and 2PQ and Q squared using these values collectively, we find that, yeah, it adds up to 1. So then the next question is, so that it is in Hardy-Weinberg equilibrium, does that mean that you expect them to change? And well, no, by definition, you would not expect any genotypic frequencies to change, because as long as these two values, and really this is the crux of the whole thing, if those two values, if they are in Hardy-Weinberg equilibrium, they must be constant. If those two values don't change, then they're the only thing that you plug into this equation. Those are the genotypic frequencies. There's no way that those things can change unless something changes in terms of P and Q. And just as a reminder, there is a way to show a situation in which you can have a population, let's say a really small population, in which we just have something like 10 individuals, we're using bees here, 10 individuals, and it could be that, in that population, 5 of those individuals are homozygous dominant, 2 of those individuals are heterozygous, and 3 of those individuals are homozygous recessive. You can do 2 things here. One is that you can directly calculate the allele frequency for the individual alleles based on their genotypic frequencies, just like we did in this problem here, and you can come up with a P and a Q value. And it turns out if you calculate that, that turns out to be about 0.6, or exactly 0.6, and this turns out to be exactly 0.4. And here's the point. It turns out that although it's absolutely true that if the P value was to change to something like 0.5, and then the Q obviously would change as well to 0.5, then without a doubt, if you change the P and Q frequencies that will directly impact your population, and the proportion of individuals who were homozygous dominant, who were heterozygous, and the proportion that was homozygous recessive, that will automatically change. Again, if you change these values and you plug them back into your second equation, you will get a different outcome. You'll find out that it likely means that it's not equal to 1, and that means it's not in Hardy-Weinberg equilibrium anymore. Things have changed. Allele frequencies have changed. The sneaky thing is that there is a way in which you can have genotypic frequencies change and not directly affect the allelic frequencies. That is, here's an easy example. So you can remove the two heterozygous individuals and change the resulting population, the subsequent population, with individuals that look like this. And if you add those alleles up, you haven't changed them. There were two big B's that I've just grouped together and two little b's that I've just grouped together. That doesn't change the total count of the number of b's that are uppercase or lowercase. So what we haven't changed are p and q. That's kind of a weird thing to think about, the fact that you can change genotypic frequencies and not influence the allelic frequencies. But it's one of those quirks and rare examples in which I certainly wouldn't throw that to you on a test, but it's to point out more of the reverse is the thing that we think is critical for you to remember, is that if you do change the p and q values, you will influence automatically the genotypic frequencies that we've listed here. Okay. So the next problem, we're going to look at people who can taste and can't taste a certain flavor. In this case, we can represent, again, our allelic frequencies P and Q. We can represent the P to represent the dominant allele, uppercase T, and the Q to represent the lowercase t for the frequency of the non-tasting or recessive allele. So we're going to pull out this equation to solve what we need to solve for. But the thing is, we're really only given one bit of data, and it's that we're given something about the recessive phenotype. That is, 37 out of 125 individuals are of this genotype, because that's the only one that's possible to be non-tasting. What does that mean? That means that turns out to be a value of 0.296, and that also is the same as that genotype, right? This genotype is represented in Hardy-Weinberg's equation as this. So if you want to extrapolate that, or not extrapolate, but if you want to solve for how can we use this to actually calculate something about the frequency of the recessive allele? The recessive allele frequency is just Q. So to solve for Q, you take the square root of Q squared, or you take the square root of 0.296. And if you do that, you'll find that you get an answer that's going to work to about 0.54. So that's the frequency of the recessive allele Q. And of course, once you have that, you can then go forward. You could solve for the frequency of the dominant allele. If you wanted to know P, then it would be just 1 minus Q, and you could solve for that, and you could take that amount. You could then take 2PQ, and that could tell you the frequency of the heterozygous individuals. You could take P squared, and that could tell you the frequency of the homozygous dominant individuals. So lots that you can do once you just get that first number. But that's all you're just asked to find out the frequency of the recessive allele, which we did right here. So last problem, you get 100 seals, and we're looking at, I guess, a co-dominant model here, because we have seals that are black, but black only if they have the two dominant uppercase W's, and we're actually not really concerned with anything about the black phenotype or the genotype. We're concerned about this heterozygous genotype, and the phenotype being the spotted phenotype. So 100 seals, 80 of them are black. You can imagine we're going to do something very similar to what we just did in the previous problem. We know that 80 in 100 individuals represents this dominant, homozygous dominant genotype, but that also is represented in terms of the Hardy-Weinberg equation using that factor. So we know that's 0.8, and we know that one other thing we can do is solve for P by taking the square root of 0.8. And when we do that, it turns out that we can find out that P, just on its own, is 0.894. That's wonderful, because the next thing we need to do is figure out Q. If you want to know something about how many seals are heterozygous, what you're really trying to say is how can I get the frequency of individuals that have that genotype, right? This genotype, uppercase, lowercase w, is represented in Hardy-Weinberg equilibrium by that equation. At least this is what we would expect if these populations of seals are in Hardy-Weinberg equilibrium. So the next thing we need to do is solve for Q. So for Q, you're just going to take 1 minus P, or 1 minus 0.894, and that can get you your value for Q. 0.106. So we're almost home. We know Q, we know P. The last thing to do to solve for the proportion of individuals that will be heterozygous is 2PQ. So that's going to be 2 times 0.894, which we solve for here, times the value for Q, which we just solved, is 0.106, and that's going to turn out to be 0.19. I'd say stop here, but there aren't 0.19 seals. What this represents, again, because we're talking about a Hardy-Weinberg variable, this is the frequency or the proportion of the overall population. So there are 100 seals in the population, so you need to multiply this by 100 to figure that you would expect 19 spotted seals in this population. That's how you get to the answer for A. And the last answer here, the last question on the homework set, or the recitation, is just to figure out how many seals are white. And since white is just represented by the lowercase w, we know that in terms of Hardy-Weinberg is not just Q, but Q squared. We solved for that in the earlier problem. We found that was 0.106 was the value for Q, so we can square that and say 0.011 is the frequency or the expected proportion of individuals who will be white. And just as we did before, there are 100 total individuals in the population, so you could say this is about 1 seal. So there's not a whole lot of albino seals out there. So that's how you do these Hardy-Weinberg problems. Again, just 2 equations that you're manipulating each time, and hopefully that's all you need to know.